Okay. Yeah, so if any of you want to like pursue the mouseless thing, I think you should. It's a lot of fun, especially if you go, you could out Linux on the, oh yeah, sure. It is possible. And there are people who have done this. So what I would probably do though is I'd probably run it as a dual boot if I really wanted to, but my Surface just doesn't have enough space really for that to be worthwhile and efficient. So as a general, I've chosen not to go that option. And then, yeah, it's a little bit shady. Like the touch interface for Linux on the Surface is like Linux's touch interfaces are still need a lot of work, right? It's not just about putting, Linux on the Surface, right? I still want to be able to write on it. So that's really the issue there. I mean, it's coming along, right? But again, when you're open source and everyone's just doing it through volunteering, things don't tend to move very quickly, but that's okay. I really want them to have like a proper Linux phone though, right? Not just Android, but I would take Android over iPhones. Anyway, whatever, it's just your personal preference, right? And I just happen to hate those things. That's just me. Okay, so we're going to do some antiderivatives today. And basically the idea is that up until now, so we've defined the integral. We've talked about how to determine whether a function is integrable or not, right? We've talked about a little bit about measure. And really, we talked about measure almost exclusively so that I could introduce that theorem, which is, if you have measure zero discontinuities, then you're integrable. But at the end of the day, for the 3 weeks or so that we've been talking about this, 2.5, I guess, this is like the end of the 3rd week. At no point have we ever talked about like how you actually compute these things, other than finding this special number that's between the upper and lower Darboux sum, right? So we actually should talk about how to compute these things. And that's not, it's a pretty slick thing, it turns out. I think, the slickness is lost on a lot of people because, I'm going to show you the fundamental theorem of calculus, which teaches you basically how to compute these things. And it's not going to seem crazy, but if you go back and you look historically, like differential and integral calculus were developed independently. And then the fundamental theorem of calculus linked them, right? And so, spoilers, differential calculus is related to integral calculus. But yeah, so I mean, if you don't have that historical perspective, it maybe doesn't seem as crazy. Anyway, so in order to do this, we need to be able to talk about what antiderivatives are. So let's just dive in with a definition. So definition. So if f, I guess I should probably do this on an open interval, AB to R, we say that a function big F on the same, right, exactly the same interval is an, okay, not the, is an antiderivative of little f if, nope, that's not. If the derivative of big F is little f. Right? So little f is the derivative of big F. That would make big F an antiderivative of little f, right? So that's the definition there. It's just, going the opposite direction in the differentiation ladder. So for example, and because you're 157 students, we'll start with maybe a more complicated example than I would give the other students. So for example, if f is the square root of x, then actually, let's see if any of you can do it. So I suspect some of you have seen this before. Can anyone give me an antiderivative for the square root of x? Any antiderivative that you want. There are multiple. There are, in fact, infinitely many. Anyone? So 2 over root x, that's close. Or actually, no, that's the derivative though, Adam, right? So we're actually going the other direction. Sophia, very close, but the derivative of x to the 2/3 is, okay, Yvonne, very close as well. Yeah, there you go, 3/2. Right, is an antiderivative. And the great thing is you can always check. Yeah, exactly. You can always check your answers. Oops, no, wait, this is, yeah, this should be 3/2 and 2/3. Yeah, there we go. There we go. No, not at this point. So I'll explain why, like why we wouldn't put the plus c. So I've just asked for an antiderivative. The plus c is when you're trying to encapsulate all possible antiderivatives, right? So I'll kind of mention how that comes in. So this is an antiderivative, and we can check it, right? We can just like differentiate this function, and if we differentiate it, right? And again, you can always check your answer. So indeed, right, f prime of x. So what do we have? We have like 2/3. And then when you do the power rules, that would give me 3/2 x to the 3/2 minus 1. So the 2/3 and 3/2 cancel, and we just get x to the 1/2. And yeah, that's the square root function, right? But, right, there are other antiderivatives that we could have used as well, right? So notice, I'm going to call it something else, maybe f hat. 2/3 x to the 3/2 plus, 100 is also an antiderivative. Right? Because the 100 doesn't contribute anything. When you differentiate, the 100 would just become 0. And so it's evident that like the choice of constant makes no difference, right? Instead of using 100, you could use -70, you could use pi, you could use pi to the power of e, whatever constant you want there, right? So this has a couple of things. So one, antiderivatives are not unique. Right? There are, in fact, infinitely many of them, one for every real number, right? So there's an entire uncountable collection of antiderivatives. What was it? Oh, wait, I was going to make 2 notes here. So antiderivatives are not unique. What was the other note? I don't know. It's something like maybe any constant could work. So any, I'm pretty sure there was another comment, but I don't remember what it was going to be. So if, maybe let's say this. So if f is an antiderivative of little f, so too is f plus c for any c in R, right? So adding a constant is definitely not going to change how the derivative behaves. So yeah, take an antiderivative, tack on a constant. All right. So what things can we immediately conclude about antiderivatives? Well, so basically, because we know that derivatives are linear, antiderivatives are also going to be linear. And that is a direct consequence of the fact that derivatives are linear. So if f and g map a, b to R have antiderivatives, capital F and capital G respectively, then 1, capital F plus capital G is an antiderivative of little f plus little g. All right, and think about how you'd prove that. It's very easy. And 2, c times f is an antiderivative of c times little f for all c in R, right? And the proof is so easy, right? Like I'm only going to do the first one because it's just not even worth doing. And what do? Well, if you want to check something's an antiderivative, differentiate it and see if you get what you want, right? So if we differentiate f plus g, maybe I'll put the x's in. right? So what does that give us? Well, we know differentiation is linear, right? And then we know big F is an antiderivative of little f, big G is an antiderivative of little g, right? And that's exactly what we wanted, right? If I differentiate big F plus big G, I get little f plus little g. So yeah, right? Big F plus big G is an antiderivative, right? 2 is an exercise, but hopefully you can just see how you would do it, right? You literally just differentiate C times F, and you know that you can pull that scalar out when you do the derivative, and boom, you right, you have it. So that's nice. That's a nice little tool. Of course, you can imagine that one of the problems that we're going to face that when we actually are trying to compute antiderivatives, because that's a lot of what we're going to be doing for the next little bit is computing antiderivatives. The linearity thing is nice, but it's not going to be the main obstacle that we face when we're actually trying to compute antiderivatives, right? So keep this in mind, but this isn't sort of like the big deal, right? This isn't the important theorems that we're going to need when we try to compute these things. Okay, so now there's a natural question, which is, okay, so we know that antiderivatives aren't unique because, you know, we can tack constants on. Okay, and so the question is, well, is there any other way that antiderivatives can fail to be unique? Like, is the constant the only problem that we can run into, right? So other than an additive constant, is there another way that antiderivatives could fail to be unique? Right? Like, could you somehow get a completely different function out of this? And the answer is no. Okay, so the answer is no. Okay, so we're going to do a theorem in a second, but basically the only way that an antiderivative fails to be unique is by adding a constant. So in some sense, there's like a meat and potatoes portion of your antiderivative, right? The main function itself, and then every other antiderivative is just some additive constant. Now that doesn't mean that there's a special antiderivative and then you just add a constant on, right? So for example, if we go up here, it might be tempting to say that like this is the correct antiderivative, right? And then everything else you just add 10 or add some sort of constant to it. It turns out that's not the case, right? We can't say that this is somehow the right antiderivative. And I'll give you an example in a second of where that goes wrong. But let's first give the theorem which definitively answers this question, okay? So if f is a function and let's say I give you two antiderivatives, f1 and f2, then there exists a constant c such that f2 is equal to f1 plus c. Okay. What is, Adam? So, I mean, it happens to be a special case where, yeah, we took the constant to be 0 in that case. But like I said, I'll give you an example once we prove this theorem of two different functions that both look like the constant is 0, but the constant's not 0, right? And so we can't definitively say which of these should be the real antiderivative. And so hopefully if you stare at this proposition for a second, you can convince yourself that this is precisely the statement or the answer to this question above. It says, if you give me any two antiderivatives, right, any two antiderivatives, then they're related up to a constant, right? The difference between them is just one of them is the other one plus a constant. So this says that that's the only way that antiderivatives can fail to be unique. If somehow the antiderivative, so let's say we have an antiderivative of the square root of x, And we said it's 2/3 x to the 3/2. Maybe there's some sort of other function out there, some sort of like weird trigonometric function, which when you differentiate it, a bunch of things cancel and you also get the square root of x. Well, if that happened, then those two things would have to be related up to a constant. And that's just not going to be possible in this case. So the only way that we can fail to be unique is by this, the presence of this additive constant. Okay, so that's what this theorem is saying. Again, the proof isn't too bad. It's this typical trick, just like when we were doing mean value theorem and intermediate value theorem, is you're trying to prove something on, this relationship between these two functions. So what you should do is create a new function, which is their difference. Right? You don't always have to do this, but this is kind of like the nice way to do this. Right? So I'm going to define h to be the difference between these two things. Okay, and then what do I know? So the special thing I know is that f1 and f2 are both antiderivatives for little f, right? So that suggests that I should differentiate at h. And if I do that, what do I get? So I get f of x minus f of x, which is equal to 0. Exactly. Yeah, we want to show that h is a constant. And you can see that this is exactly what's going to happen, because when I differentiate h, right, I get that it's everywhere 0. And one of the things that we proved, I'm pretty sure we did it, but remind me if we did it, otherwise I'll prove it now. One of the things that we did when we proved or talked about the mean value theorem is that if a function has a derivative which is everywhere 0, then it had to be the constant function. Did I prove that? So hence we got that f2 h of x minus f1 of x is equal to c, i.e. f2 of x is equal to f1 of x plus c. Yeah, okay, great. And if not, like, do it as a quick exercise for yourself right now. Again, it's just the mean value theorem. Like literally just apply the mean value theorem and you basically get your result. It's a very quick proof. Okay. Okay, yeah, like I said, try it. It's one of like the simpler applications of the mean value theorem, right? You get f of b minus f of a is f prime of c times b minus a, but you know that the right-hand side is entirely 0. So now you've proved that f of b is equal to f of a, and that applies for any b and a in the interval, so the function is identically constant. That's how you do it. Okay, and if you want, you can go back and try and see if you can find the lecture where we did it, but yeah, okay. So yeah, like I'm pretty sure it's one of the first things we would have proven after the mean value theorem. I might have skipped it for whatever reason, but yeah, I'm pretty sure it's there. Okay. All right, so let me give you an example of where it can feel as though the constant is equal to 0, like that there's somehow, yeah, as if there's somehow a special function, and then everything else is just actually adding a non-zero constant onto that. Okay, so what I'm going to do, let's take f of x to be a, whatever domain you want. I'm going to take it to be sine x cos x. Okay, can anyone think of an antiderivative of this? Now, some of you might actually know the trick. There's kind of a trick, but you can kind of do it by inspection as well, right? Like if you think about what is the derivative of sine, what is the derivative of cosine, you might be able to come up with an example on your own. So has anyone seen an antiderivative of this? Okay. Yeah, Alexander. Yeah, you definitely actually do have one. Okay, sure. Let's write that down. So the function's f1 of x. So what you did is you actually said, I think you used the following trick. So you said, you're using the identity 2 sine x cos x is sine 2x, right? And then, so therefore sine x cos x is 1/2 sine 2x, right? And then you said, okay, well, this thing's not too hard to anti-differentiate, but I feel like I'm getting -1/4 when I do this. Am I crazy? Right, because I have to account for that too. Yeah, okay. But yeah, so absolutely, Alexander, that is a great example. So that's a nice kind of clever one. And of course, we can throw any constant tone to that as well. Does anyone have another one? How about right? Think about it. Just chain rule that thing and see that you get it. Okay, there's another one. How about that? All right, that works as well. You can just differentiate all of these and check. So all of these look as though, we're just adding a plus, c is equal to 0 here, but that can't be true. They can't all correspond to some, mythical main antiderivative and then adding 0 to it. That can't be true. But nonetheless, even though these functions look different, the answer is they're all the same up to a constant, right? You'll have to play around with some trigonometric identities a little bit in order to make that work. Oh man, what is the one for cos 2x? I'm trying to remember what the trig identity for that one is. You caught me unremembering. So the double sum identity, which is how to get from cos 2x back to does anyone remember the double sum identity for cos 2x? I don't remember it. Oh, it's cos squared minus sine squared. Yeah, okay. So let's see. So cos squared minus sine squared. Okay, so F2 and F3 are clearly related to each other, right? So we have that 1/2 sine squared x plus 1/2 cos squared x is equal to 1/2, right? That's the Pythagorean identity, i.e. We are going to have that F2 of x is equal to F3 of x plus 1/2, right? Beautiful. Yeah, Sophia, that's perfect. And then, so from Sophia's identity, that's what it's called now. So we're going to have what? F1 of x. So that's -1/4 cos 2x, right? So that's -1/4, and then what is it? 2 cos squared x minus 1, right? So that's equal to -1/2 cos squared x plus 1/4. And yeah, well, that's exactly F3. Oops, F3 of x plus 1/4, right? Or if we take cos squared minus sine squared and use the other trigonometric identity, so the 2 cos squared minus 1 comes from plugging in sine squared is equal to 1 minus cos squared, right? So if we do the other one and we do cos squared is 1 minus sine squared, then we would get also -1/4 1 minus 2 sine squared x, right? That's the other one of those. So again, this time that's -1/4 plus 1/2 sine squared x, which is -1/4 plus F2 of x, right? So even though these things all looked different, right? They look like they were different functions. They're all related to each other just by up to a constant, right? So yeah, we can't say that there's somehow some distinguished, let me just put this in here so I can circle it. We can't say that there's some sort of distinguished antiderivative and everything else is just, adding a non-zero constant to it. All three of these things look like there wasn't a constant, right? But they're all the same function up to a constant, right? So we have to be a little bit careful about that. We can't just kind of blindly make those things. Now you can see here, this is really going to tend to happen with trigonometric functions or any functions in which you have some sort of identities which relate them. It's probably not going to happen with polynomial functions. Polynomials just aren't that interesting, right? Like we don't have anything which relates x squared to x cubed up to a constant, right? Like that doesn't tend to happen. But because we have the Pythagorean identity with trigonometric functions, that really unlocks a ton of trigonometric identities. And because we have a ton of trigonometric identities, we potentially have a lot of antiderivatives that look the same, or rather that look different but are secretly the same, right? So just something to keep in mind there, especially when you start playing with trigonometric functions. You might get different answers, especially if you compare your answers to a classmate. You could get different answers, but it turns out your answers are actually the same up to a constant, right? So just be careful of that. Okay, so actually here, somebody tell me, just as kind of like a little aside. So what we just did up here is an example of having a function little f, which looked like a function times its derivative, right? Right, because the original function up here was sine x times cos x. That looks like a function times its derivative. So if f of x, maybe let me just move that over so I can put the word if in here. So if f of x is a function times its derivative, what's an antiderivative? So you get a function times its derivative. Can you somehow think of what an antiderivative of that function might be? No one? Ah, right. Okay. So it turns out we don't. Okay, it is kind of chain rule-y, right? But okay, can anyone think of where would you see? Yeah, how would I do this one? Exactly. Right? Like that works. Right? You would use chain rule. The 2 would come down to cancel out the half, and then you would just keep your g of x and multiply by the derivative of the inside, right? And then that would give you g prime. And that's actually what happened here, right? That's how I got f2 and f3. I said g of x is sine, so g prime of x is cosine. That gave me f2. Now, the funny nature that trigonometric functions satisfy, you also could have let g of x be cos x, and then f3 of x is negative sine. And that's okay. It doesn't work out perfectly because we get that extra minus sign, but we're not worried about that extra minus sign because, again, we know we can just pull scalars out of antiderivatives, right? That's what that previous proposition said about antiderivatives being linear. So again, you don't need to worry about constants because you can always multiply a constant in order to make everything work out. And hopefully already you get a much deeper appreciation for how much harder this is, like anti-differentiation is than differentiation, right? Like if I gave any of you this function, no problem differentiating it, right? I think every single person in this class would just crush this and would have been able to grind that out really, really quickly. But when I ask you to say, what do I differentiate to get this thing, g prime, it's much harder, right? And so even the tools, and again, we're going to talk about a couple of tricks that we can use in order to help us figure out what antiderivatives are, but it's still just more complicated just because it turns out like even simple looking functions can become extraordinarily complicated in their antiderivatives. And then it turns out there are some functions that just don't have elementary antiderivatives. Okay, so there are functions which do not admit elementary antiderivatives. Okay, and elementary here means, and even though, in this class, okay, like 1 over x, that is cheeky and not cheeky. It depends. It depends, right? You're right. In some sense, it's kind of arbitrary about what we do. It's tricky. It is tricky. So, for example, lots of classes will, like, we haven't talked about logs and exponentials, right? And we've done that for a very particular reason. It's because it's very hard to define those functions rigorously. Okay, and the best way to define the logarithmic function, it turns out, is as an integral, right? So if you're in a class, especially an early transcendentals class, I think you've all learned about logs and exponentials in high school, but they probably taught you very poorly and didn't give you a super rigorous definition, right? Like, what is e to the pi? Like, how do you even compute that, right? What's the rigorous definition of e? Actually, let's do that right now. Can anyone tell me what is the rigorous definition of e? Right? Like Euler's number. What is it? Okay, so Stephen, you have an interesting idea, which is to prove that it is the function whose derivative is itself, right? Okay, how do you prove that such a function exists? But Jinjin, if you take that route, you need to know what a series is and how to tell whether a series converges, right? Simon, you want 1 plus 1 over x to the x, I'm pretty sure. So your definition is interesting because that's actually the equivalent thing of saying it is the limit of continuous compounding interest, right? So that's actually what that definition is. But how do you prove that limit exists? Okay, so there are a couple of perfectly fine ways of doing it. So a couple of, okay, wait, let me, okay. Now we've got bonus number 2 because we're getting distracted here, but I think that these are all cool things. So what is the definition of e, or if you want, or e to the power of x, right? Like that function, okay? So we've got a couple candidates. One, it is the function f of x such that d dx f of x equals f of x. Okay, so what I want you to think about is 1, prove to me that such a function exists, and 2, prove to me that that function looks like 2 to the like an exponential function, right? And then even once you've proven it exists, proven that it looks like, maybe let me write this down. A, prove this exists. B, prove this looks like a to the x for some a and r. C, derive e. Okay, this ends up being really hard. Like, this is a lot of work. You're right, the zero function. So you'd say like it's the non-zero function, right? That satisfies this. But also, here's an important question. What is this? What is a to the power of x? Does anyone know what the definition of a to the power of x is? Like, can you just do this? Is this allowed? Is this legal? Okay, but now you're kind of recursive because what's the definition of log? It's usually the inverse of e to the x, right? So like we probably can't use logs to do this problem if logs don't exist yet because we don't know. Do you know what I mean? But more importantly, okay, so let's say that we could define this. You're right. And this is a great kind of point. Repeated multiplication doesn't make sense if these are real numbers, right? So I believe any of us could define a rational number to the power of a rational number. Hell, you could define a real number to the power of a rational number. That's no problem, right? So we know we can define a to the power of, let's call it q, where q is a rational number. Okay, I believe that all of you could do that and know what it means, right? So a to, if I took pi to the power of 3, that means multiply pi by itself 3 times. And then you extend that to the rationals by including nth roots, right? So pi to the power of 3 halves is pi cubed, and then the square root of whatever that number is. And for that matter, we haven't even proved that nth roots exist, but let's suppose that they do. What does it mean to take pi to the power of square root 2? Like, if that number is not rational, if the exponent is not rational, what does that mean? Right? And so I think a lot of people forget, because you can plug this into your calculator, right? You can plug pi to the power of square root of 2, but of course your calculator isn't actually doing that computation. It's rounding those numbers. It rounds pi and it rounds square root of 2 so that they become rational, and then does this computation, right? So your calculator isn't actually doing that. Right. Yeah. So Yvonne, that is that. No, but we can't do that because we don't have e and ln, right? Like, how do we, right? In this setup, we're trying to figure out how to define the exponential function. And so how can we can't define a to the power of x in terms of e and ln if we're using it, you know what I mean? Like, it's a circular definition. We don't have access to e and ln in this problem because we're trying to define e. Okay, so hopefully you can see, like, there are a lot of problems trying to do it this way. It's totally okay, but there's some things you have to assume. Okay, and by the way, the answer to this question is the way that you have to define a to the power of x is you take a sequence of rational numbers which approaches your real number x. Okay, so you find a sequence, and we're going to talk about this later. So you've got a sequence of rational numbers which converges to x, and then you define a to the power of x as the limit as n goes to infinity of a to the power of qn. Okay, so if you want to be able to do this without using exponentials and logarithms, say because you're trying to define an exponential and a logarithm, this is actually how you have to define the exponential function, right? And you can imagine this is quite messy to work with. Okay, so that's one way you could define e to the x. So what did we had another one. So someone had, like, the limit as x goes to infinity of 1 plus 1 over x to the power of x. Okay, it turns out this is equal to e. So I want you to prove this exists. Okay, and then compute its limit. So this isn't impossible. It turns out that this is doable, but it's still quite long. So first of all, if you actually want to prove that the limit exists, you're going to have to use the monotone convergence theorem, which I don't think we've really talked about, but I basically made you prove it at one point. But it's basically, if the function is monotone increasing and bounded from above, then the function must have a horizontal asymptote. You need to use that. So you have to analyze the function 1 plus 1 over x to the power of x. But again, what does to the power of x mean? So same problem here. So 1 plus 1 over x to the power of x, argue that this function is actually, which one is this? This one is monotone increasing and is bounded from above, therefore its limit exists. And then in order to be able to compute its limit, you need to prove some sort of hairy L'Hopital's theorem. Okay, so it's quite laborious. What was the other definition? Did somebody have another one? The derivative. Oh, and the Taylor polynomial. Yeah, which is, like, probably not the way you want to go, because that requires convergence. And then even worse is if you want the function e to the x, requires that you understand what uniform convergence means. Okay, and we're going to talk about this. I'm going to define uniform convergence for you. It's not easy. It's not obvious, right? But by Picard's theorem, what proves that there's only one function that its derivative is equal to itself and e of 0 is equal to 1? I don't know what Picard's theorem you're talking about. There's usually two Picard's theorem, and neither of them are real analytical results. They're usually complex analytical results, right? But either way, you have to prove this. So anyway, along these lines, which is this great question, is there is a fourth definition. And this is some weird notation, but whatever. Okay, sure. I mean, I'll look up what that is. But by this, right, basically you define ln to be this integral, and then e to the x is its inverse. So in this case, if we take this path, then yes, this function actually does not have an elementary antiderivative. Okay, let me just double check Picard-Lindelof. Existence of uniqueness. Sure. I see what you're saying. Yes. So right. So that's not what people tend to call this theorem. So this theorem that you're using here is that this theorem exists, is the existence uniqueness theorem of ordinary differential equations, right? That's what you're using there. So let me see if there's any issues in this. Yeah, exactly. If you check the wiki in this, it's explicitly called the existence and uniqueness theorem. So exactly, if you want to prove this exists, you have to prove existence uniqueness first. And there's no way we are proving existence uniqueness. Do you know what I mean? Like, this is, you don't just get to claim Picard-Lindelof holds in this class. You have to prove Picard-Lindelof. And if you want to do that, you have to go take the second-year specialist ODEs course, and I think spend 2 weeks doing that proof, right? So like that proof is not in any way obvious. So it turns out number one, despite kind of being intuitive, is actually the worst possible way of doing it. Right, don't do it from an ODE's viewpoint. Okay, so yes, if we take, as in this class, we are going to assume that 1 over x does not have an elementary antiderivative. However, there are some classes where you would say that that's not the case. So by elementary here, we mean you can write it in terms of polynomials, roots, exponentials, logs, trigonometric functions, and then all their sums, products, quotients, and compositions. Okay? So a function does not have an elementary antiderivative. If you cannot write it, it's antiderivative. So its antiderivative might exist. Exactly. Almost everything that you've learned in high school, right, is a polynomial, a root, an exponential, logarithm, trigonometric, sum, a product, a quotient, or a composition of these things. However, there are some very straightforward functions that do not have elementary antiderivatives. This function does not have an elementary antiderivative. Okay, e to the negative x squared, and you could use positive x squared as well, but I use negative x squared for a very particular reason. E to the negative x squared does not have an elementary antiderivative. Okay, this function is integrable. Oh, actually, we haven't talked about fundamental theorem of calculus yet, so we don't know that those two things are related. But basically, this function does have an antiderivative. Okay, you can draw it, you can plot it. The function exists, but it is impossible to write that function as a combination of polynomials, roots, exponentials, logarithms, trigonometric functions, and any of their basic combination of those things. Why is this function so important? This is one of the most important functions in the world. Why is this function so important? Does anyone recognize it? If you're not certain what this function is, just graph it. Exactly, this is the normal distribution. right? Anytime anyone talks about bell curves or anything like that, yeah, okay, so, I realize some of you guys haven't like taken stats yet, but the normal distribution, or the Gaussian, it's sometimes called, is the bell curve, right? So it is basically, what is it? If you statistically ran an experiment where you had a bunch of identical and independent experiments, then most things follow a normal distribution, right? Where everything is within 3 standard deviations of the mean, blah, 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 blah. It is the error function. The error function is technically a little bit different. So the error function is, I forget what this constant is. I think it's like 2 over root pi, integral from -infinity to x e to the negative x t squared dt. That's the error function. So there's a bunch of things in here that we don't understand yet. One, where the heck did this come from? How is there a pi in this, right? You should look at this and you can be like, no, there should not be a pi in there, but there is a pi. One, what does this mean? Because we have said that this is not possible. You're not allowed to do this, right? So we have to figure out what that means as well. So there are at least 2 things in here that we don't know what they mean, but that is what the error function is. It's the integral of that thing. Right, it is an improper integral, and we have to talk about what an improper integral is, right? Yes, exactly. It's a normalization constant. So strictly speaking, it's not necessary. And I think there is actually like a weird error function that doesn't actually have that. But basically, the purpose of that constant is to normalize it. So if you actually compute the integral from -infinity to infinity of e, okay, here's why this should hurt your brain. Okay, you should stare at that and you should be really, really upset right now. Because again, where the hell does the pi come from, right? Like, this is an exponential function. If you think about this, again, you all can probably reasonably guess what this improper integral is. It's somehow the area under the whole curve. And that might not converge for arbitrary functions, but the bell curve, becomes 0 very, very quickly. So it does turn out that that area actually converges. And but it converges to the square root of pi. What? Right? Like, how is that? Where is the pi coming from? And this goes to some crazy hidden secret fact, okay, that I promise you I will start to pull the covers so you can see what's happening. The exponential function and the trigonometric functions are the same thing, okay? This thing, and this thing are all the same. Right? They're all in the same big happy family. Right. But again, so I think some of you, right, like, about like Euler's theorem and this sort of thing. But if you haven't thought about the profoundness of this statement, then you should, right? Yeah, exactly. What do I mean by the same? So we'll have to talk about that a little bit. But think about what the trigonometric functions are, right? There's some sort of relationship on triangles and circles or whatever the case might be. The exponential function is not related to that in any way, shape, or form, right? There's no discussion of circles. There's no discussion of triangles when you define e to the x, right? None of these definitions that I've given you have anything to do with circles or triangles. No definition of even if you ignore e to the x and you take something like 2 to the power of x or 3 to the power of x or just some real number to the power of x, none of that conversation has anything to do with trigonometry. But pi is a trigonometric constant, right? And cosine and sine are trigonometric functions. How are these things related, right? How could they possibly be the same thing? The answer is, yeah, turns out they're the same, right? And the answer to this okay? And the reason why it's not evident to us in the real numbers is because in order to see that they're the same, we need the imaginary number, right? But it turns out if you you do everything in the real numbers and you say, okay, what's the correct way of talking about these things in a complex analytic sense, and you start throwing, this number I into the situation, turns out, yeah, the exponential and the trigonometric functions are the same function. I can write e to the x in terms of cosine sine. I can write cosine sine in terms of e to the x. No, it's like, the point is that it is basically the same. Yeah, it is the same function. It behaves differently. It behaves very differently. Just like sine x, when you are allowed to plug in a complex number, behaves completely differently than the real sine x. But first of all, if you restrict the exponential function, the complex exponential function, to the real numbers, it behaves the exact same way. Second of all, the function is analytic and has the same Taylor series, right? The definition of e to the x, if you take it to be this thing, this is the definition of e to the x, both for the real numbers and for the complex numbers. It's the same definition. It's not just notation. It is the same. It's the same thing. It's just, in one case, x can be